Okay, the recording just started. So Paula, I hand over to you.
Thanks. So welcome everybody to this Laws of Nature seminar today. Our speaker today is Anirudh Gundhi. He's currently a postdoc in the working group of Angelo Bassi at the University of Trieste. And he will speak about his current work. I think it's about decoherence due to vacuum fluctuations. So please.
Thank you, Paula. And so thanks everyone for coming, and especially to the organizers for organizing the series. So the topic which I want to talk about is decoherence due to vacuum fluctuations. It's the project which I did during the last phase of my PhD, and I'm still continuing to work on related topics. So essentially, let's say the question that I wanted to address during this, so maybe I can, yeah. So the question which I wanted to address in this work is to imagine that if we have an electron in a superposition of two different spatial locations, would it decohere just due to its interaction with the vacuum fluctuations, where the vacuum is now understood in a quantum field theoretic setting? So now we know that in QFT, essentially every field, like for instance, the electromagnetic field, is considered to be a collection of harmonic oscillators. And we know that for a harmonic oscillator in its ground state, although the expectation value of the position or the momentum operators are zero, their variance is not zero. So in this sense, if we consider the electromagnetic vacuum, we know that the electromagnetic field operator, for instance, the electric field operator, would not be identically zero as it would be classically. So the question becomes that if I now have an electron in a superposition of X and X prime, would this non-vanishing electric field operator sort of interact with the electron and measure its position and lead to decoherence? And the question is interesting from various point of views, but also because of what has been said about this problem in the past. So if I can shift this, okay. So for example, I am quoting this work from Breuer and Petrocione, which appeared in 2002. And so they say specifically in their conclusions that a result of particular interest from a fundamental point of view is that coherence can already be destroyed by the presence of electromagnetic vacuum if superpositions of many particle states are considered. A particular conclusion which can be drawn from this picture of decoherence in QED refers to various alternate approaches to decoherence and the closely related measurement problem of quantum mechanics. In recent years, several attempts have been made to modify the Schrödinger equation by the addition of stochastic terms with the aim to explain the non-existence of macroscopic superpositions. It is interesting to observe that the decoherence effect caused by the presence of quantum field vacuum yields a similar timescale in a completely natural way without the introduction of new physical parameters. Thus, QED indeed provides a consistent picture of decoherence, and it seems unnecessary to propose ad hoc new theories for this purpose. So just to give you a bit more context in this work by Breuer and Petrocione, they essentially considered the same problem in which you take an electron in the presence of the electromagnetic field, but the electromagnetic field is taken to be in its ground state. So essentially the absolute vacuum. And their conclusion was that indeed there would be some finite decoherence effect due to the interaction with vacuum fluctuations. And then they posed this conclusion as a possible resolution to the measurement problem of quantum mechanics. So again, I think all of us know about this problem, but just to give a brief summary. So at the end of the day, what we want to explain is why we do not see a chair in a superposition of here and there, given that the Schrödinger equation would sustain such a position at all times. And the program of decoherence, the way it solves this problem is to say that practically any system which you look at is an open quantum system. So when you look at the chair, you are focusing on chair, but in principle, it's also interacting with its environment, which could, for example, be the gas molecules which surround the chair. So although you initially prepare the chair in a superposition, the environment of this chair monitors the location of the chair And locally, the chair would always appear to be at a localized state rather than in a superposition of here and there. It would be either here or there. However, the program of open quantum system does not solve the measurement problem for the global wave function, which is the wave function of the chair and its environment. So this wave function of the universe, if we put it more dramatically, would always remain in a superposition. And now with this work of Breuer and Petrocione, what they are concluding is that if, for instance, vacuum fluctuations do lead to finite decoherence effect, that even this global wave function would be localized and the measurement problem would be solved within the standard framework of QFT. So you don't need to go to the GRW models where you introduce non-linearities into the Schrodinger equation. And this is the main conclusion of this work. And not only them, I think there have been other works also in the past which say that there would indeed be finite decoherence due to vacuum fluctuations. But I quoted this particular conclusion because I think it is in some sense the correct logical consequence of what it would mean if there was actually finite decoherence effects due to vacuum fluctuations.
Anirudh,
Sorry.
may I pose a quick question, only
Yes.
for understanding. I mean, which time evolution do you have in mind here? Do you already have a collapse, continuous spontaneous collapse model in mind, or?
So yeah, so the quote which I take from Breuer and Petrocione when they mention these time scales, they mean similar in the sense of the time scales which the GRW model gives.
Okay, because
Yeah.
I mean, so for the Schrodinger equation, I mean,
Yes.
it is it doesn't make a difference if you have n particles, big or and small. I mean, you will have the measurement problem, yeah. So you always consider, and also tracing out environment will not help you to solve the measurement problem. Yeah, since the Schrodinger equation still has a unitary evolution, but you have already in mind that there's some kind of spontaneous collapse mechanism that's built in.
No. So I'm saying, okay, so let's say maybe it will become clear a bit towards the end. So for example, if you just consider QED, there is a natural time scale which comes up from the constant. So you have E squared, H bar, and C. And from these constant itself, you can, there is a natural time scale which emerges. Okay. And so if you take this time scale and then you multiply this time scale with the number of particles, there is a characteristic time scale over which decoherence appears in QED. So you don't even need to talk about vacuum fluctuation. So let's just say that I have an accelerated particle in a superposition. Okay. So because this accelerated particle would emit radiation, the radiation carries which path information, and there would be a certain time scale given by QED over which this decoherence happens.
But decoherence doesn't solve the measurement problem.
No, yeah, I agree. Decoherence in general does not solve the measurement problem in the sense that if you include the environment of the system which you are looking at, the global wave function would always remain in a superposition. But now what Breuer and Petrocione are suggesting is that fundamentally you imagine the vacuum fluctuations to be always outside of what you can measure. And if you do that, your global wave function, so with the chair and the air molecules included, since there would always be vacuum fluctuations outside, you would have a unavoidable source of decoherence.
Okay, I mean, I will pose a question in the end and then let you go.
Yeah, I mean, anyway, so my talk is to really against this conclusion, but I just wanted to state what they said essentially.
You are also.
But maybe to say it differently, if I understand it correctly, so Breuer and Petrocione cannot solve the measurement problem by that.
Yes.
But they can argue that by ordinary quantum mechanics,
yes,
we also cannot see interference from microscopic objects.
Yes, exactly.
Okay, just like in collapse models. So if you think you're testing collapse models by testing interference from microscopic superpositions, well, you would also not see interference according to their program.
Or I can phrase in another way to make a connection more explicit with the collapse models. So in collapse models, you have this stochastic noise, right? Which you always posit where you don't know the physical source of this noise. Breuer and Petroccioni are essentially saying that this noise comes from vacuum fluctuations.
But this is where I really can't understand it. I mean, if the time evolution is unitary.
No, it will not be unitary because they treat vacuum fluctuations as fundamentally outside of
Okay.
Yeah, so what they're saying that effectively the system which you measure, you can never measure vacuum fluctuations in the sense. So in some sense, they are making a postulate that the environment of vacuum fluctuations is something always exterior to the system that you're looking at.
Okay, but then the question is, in their view, do they have unitary evolution, or do they have
maybe this becomes clear as I go on, because so basically
that's
now
important, right? If you have unitary evolution, as Dirk says, you don't solve the measurement problem by saying you can't see interference. Okay.
Yeah, so I mean, in principle, their wave function would always evolve unitarily, so it will not collapse. But I think their point is that you will not see coherence at the global level of the wave function. So you don't really, even if I consider the wave function of the whole universe, you will not see a coherence of this global wave function, because you always have as an environment the vacuum fluctuations.
Yep, coherence and superposition are two different things.
No, I'm only making a claim about superpositions. Yeah, they are only saying about superpositions at least.
Yeah, but there is something fishy about it if the time evolution is unitary. But maybe we let you go. Continue, and then in the end we can have a bit more discussion.
Yes. Okay. Okay. So this is the setting essentially. What we want to understand. So even if you don't, I mean, so there is the fundamental angle to this problem, but there is also a practical angle. So if indeed there is some decoherence due to vacuum fluctuations, it is still important to understand this, because if for example, you are interested in testing collapse models indirectly via its effect due to additional decoherence effects, it's important to understand whether this vacuum fluctuations are already something that you are missing out in your analysis. Because if you have some decoherence effects due to vacuum fluctuations, you must subtract this before attributing any observed decoherence effects to collapse model. So there is also a practical side to this problem. Okay. So with this, we go on. So essentially, how do we approach this problem? So whether or not there is decoherence due to vacuum fluctuations, we start with the Lagrangian for electrodynamics. So you have the particle, which I model as a point particle. So R denotes the position of the electron. V naught can be an arbitrary external potential. It can also be zero if you consider a free particle. And then you have the electromagnetic field, and then you have the interaction term. So E perpendicular is the transverse electric field, and B is the magnetic field of the radiation field. And we will assume the electromagnetic field to be in its vacuum state. And again, the point is that from a QFT perspective, even in the vacuum state, the field operator E would not be identically zero. So you see here explicitly that there is interaction of the electron with this field operator. So the goal is now to describe the effective dynamics of the charged particle, taking into account its interaction with the radiation field environment. And this can be achieved by deriving the reduced density matrix for the electron. So to do so, we would use, at least I use the path integral formalism. So in the path integral formalism, I mean, I don't want to bother anyone with too many details, but the main point of view is that the path integral formalism calculates the probability amplitude that starting from a position xi at time ti, the electron is found at position xf at time t. And this probability amplitude is this probability amplitude can be calculated in terms of the full action governing the dynamics. And then you just perform the path integral with the boundary conditions fixed. And since we have these probability amplitudes, one can also express the wave function in the language of path integral. So if you know the initial wave function, you can express the final wave function at time t. again in terms of the path integral and just the full action governing the dynamics. And it's clear that if we know the full wave function, we can also write the density matrix in terms of the full action governing the dynamics and the initial density matrix psi, rho I. Now for open quantum systems, what I need to do now is to separate the system from its environment. So the system for us would be the charged particle, and the environment for us would be the radiation electromagnetic field. So here we have written for the full action that we saw on the previous slide, we have just separated the action which concerns only the system degrees of freedom from that which involves the environment and the interaction part. And now, let me just bring this tab to, sorry. And now what we need to do is to perform the trace over the environmental degrees of freedom in order to calculate the reduced density matrix. So if we do so, it turns out that the integral, this trace or the integration over the environmental variable can be calculated exactly because it turns out to be a Gaussian integral. And the outcome is that doing this trace or integrating over the environment, you get a reduced density matrix in terms of the system action that we started with, plus the so-called influence functional. So all the information about how the environment measures or monitors the electron is captured by this influence functional SIF. And what is this? This influence functional is essentially calculated or related to the 2-point correlations of the environmental operators. So in this case, these operators would be the conjugate momentum operators of the electromagnetic field, which you can essentially imagine to be the electric field operator. So what we do is that to calculate the influence functional SIF, all we need to do is to calculate these 2-point correlation of the electric field. Once we calculate this, we put this guy back in equation 4, and that gives us a perfectly formal expression for the reduced density matrix. And then having computed this influence functional, all we need to do is to then calculate the path integral. And again, the expectation value of these 2-point correlation is calculated with respect to the initial state of the environment, which in our case is the vacuum state. So this is where the initial conditions come in. So now, as I said, we know the influence functional in terms of the environmental operator. And now we only need to perform the path integral. And it turns out that this integral can be explicitly performed or done very easily up to second order in the charge E. And so if I compute equation 4 up to second order, we get the following master equation. So the time evolution of the reduced density matrix takes us basis independent form, which is given by these 3 lines. So the first line is the free evolution or the Liouville von Neumann term. This is how the system or the electron would evolve if there was no interaction with the environment. The interaction with the environment is captured by the second and the third lines. So the second line involves the so-called noise kernel. And you see that here it has the double commutator and position operator with the reduced density matrix. And this double commutator term is essentially what is responsible for decoherence. And then there is the third line, which involves the so-called dissipation kernel. And this term, for example, would quantify how the electron loses energy to the environment. So for example, if we have an accelerated electron, it would emit radiation to the environment. And that effect is essentially captured by the third line. So the second line tells us the amount of decoherence, and the third line would, for example, be responsible for radiation reaction at the level of the electron. The guy here, X with a subscript HS, is understood as the position operator, but in a Heisenberg picture, whereas the position operator without any subscript is the standard Schrodinger operator. So for example, if I consider a free particle without any external potential, this X hat with the subscript would be the same as the Schrodinger equation operator. Sorry, it will not be the same, but yeah, you know how to calculate this. So this x hat with the subscript h is the position operator, time evolved only with respect to the system Hamiltonian. So it has nothing to do with the environment. And this we know how to calculate. Yeah, and similarly, these noise and dissipation kernels, they are defined with respect to the environmental operators. So again, we have the conjugate momentum operators of the environment. And the noise kernel is calculated by computing the expectation value of the anti-commutator, whereas the dissipation kernel is calculated by computing the expectation value of the commutator of these momentum operators. So now, essentially, we have the master equation in our hands. And to really specify this master equation more explicitly as a function of time, all we need to do is to calculate these guys N and D more explicitly. And this can be done. So we know how the field operators, the QED field operators look like. It's a standard textbook expression. So we write the momentum operators in terms of the creation and annihilation operators. And then all we need to do is to calculate these 2-point correlation with the initial state taken to be the vacuum state. And when we do that, we get the standard problem that we get in QFT, which is the appearance of divergences. And to fix that, we introduce a cutoff in the calculations to obtain finite expression. And in terms of this cutoff, we see that this 2-point correlation here can be written like this, where tau is just the difference between T1 and T2, R is the difference between XT2 and XT1, and this is the standard Laplacian operator. And epsilon is defined as 1 over the cutoff that is introduced here. So now what we do is, since we are interested in the electron, which is traveling at non-relativistic speeds, essentially we can ignore this R dependence in favor of the C squared tau squared term. And then in that case, the noise kernel would become just a function of time. And indeed, you can get explicit expression of the noise kernel in terms of the cutoff epsilon, which again we saw was 1 over omega max. And similarly, the dissipation kernel can also be obtained explicitly as a function of time. So now you see that with the help of equation 12 and 13, if I go back to the master equation, here I would substitute this N and D, which I calculated, which we just saw, and that would really specify or give us the master equation explicitly in terms of time. And I think this was, for me, this was one of the new features that appeared out of the work, because although a lot of people have tried to formulate this problem, in no work did I see a master equation written explicitly, which can be used in a convenient way. So here we see that really this master equation is written in a standard form with N and D calculated how they really look like as functions of time. So now essentially what we want to do is to make use of this master equation to answer the problems that we raised in the beginning of the talk. So now we go back to decoherence. So again, coming back to the original problem, if I have an electron in a superposition of X and X prime, would it decohere due to the presence of vacuum fluctuations? And to do that, essentially, sorry to go back, essentially we would only focus on this term, because this term is the main term responsible for decoherence. And so you see that only the noise kernel plays a role essentially in computing the decoherence effects at the level of the electron. And it turns out that if we calculate how the off-diagonal elements of the density matrix are suppressed, all we need to calculate is this double integral of the noise kernel, which we computed explicitly. So we know that the off-diagonal elements of the reduced density matrix essentially tell you the probability that the electron is at X prime and X at the same time. So given a certain initial probability, we see that if this N2 is non-zero, this probability would decay with time. And this is essentially decoherence. Okay, so now all we need to do is to calculate this N2 of T, which is a double integral of the noise kernel that we calculated. And the expression that we find is the following. So first we just rewrite this off-diagonal terms in terms of the coherence length. And then calculating this double integral, we find that the coherence length for the problem that we started with has this particular time dependence. So you see that on time scales much, much bigger than epsilon, this coherence length takes a constant value, which scales with 1 over the cutoff that was introduced to perform the QFT calculation. And so the first thing is that since this coherence length is not infinite, any initial superposition that you start with will be suppressed. And the more problematic part is that this coherence length scales explicitly with the cutoff. So if I now take, for example, this cutoff to infinity, it would imply that any finite superposition that I start with would be immediately suppressed just due to the presence of vacuum fluctuations. So without any acceleration, without any thermal bath, just the vacuum fluctuations would be sufficient to suppress this superposition on arbitrary small length scales.
Anirudh, that's
Yes.
one short question, but we can really defer the discussion.
No, we can. I think it's fine. We do it now. Yeah.
Yeah, it's just, I mean, you're saying superpositions are suppressed, but what I see here is only the decoherence effect, that the off diagonals are suppressed. These are two different things, right? So, I mean, your underlying dynamics is still a unitary dynamics. I mean, the underlying dynamics is the one of the, let's say, Fock space vector of your QED that you write down, and that is unitary, and the superposition still persists. Of course, in the master equation, the off-diagonal elements of the matrix are suppressed. Yeah.
So when I mean superposition, I'm saying only at the level of the electron, not the global superposition of the function, wave function null, which also involves the radiation field. So if I trace over the environment and I'm only looking at the system degrees of freedom, those superpositions would be suppressed. So, I mean,
and I disagree here as well. I mean, somehow the basic theory is the one that you have written down in the beginning. Okay, if you write it down with path integrals or by Schrödinger equation, so it's the same. Yeah, so that is unitary. So of course, if you trace out and you find an identity matrix, and the identity matrix has the mathematical property that the off diagonals vanish, fine. Yeah, and I think this is a really fine computation that you do, but it has nothing to do with resolving a superposition.
Okay. I mean, I understand what you mean. So yeah, I mean, so let's say so what I mean is that if you perform an interference experiment with the electron, you will not see the fringes, essentially. This is what I mean. So I agree that globally, there is the superposition at the level of the electron. But for example, if I perform the same double slit experiment now with the electron, so let's say that there were no vacuum fluctuations. If I perform the double slit experiment, I get the fringes. But now in the presence of vacuum fluctuations, what this calculation is suggesting is that these interference fringes would be lost.
Yeah, let's maybe discuss in the end. I think it's not what I can tell from these equations, but let's go on. Yeah.
Well, I mean, let's say the suppression of the interference pattern is essentially measured by the off-diagonal elements of the density matrix. So this is all I mean.
Yeah, I mean, yeah. Okay, it's a long discussion, I guess. Let's defer this to the end. Yeah? But I mean, what I see here is, of course, the decoherence effect, that the off diagonals vanish. Yeah.
Yes.
And but the unitary time evolution, which is underneath, is still there, and it's unitary, and therefore it has the measurement problem. But
yeah, I mean, I'm not saying so. At the moment, it's really a practical problem. So even if I don't bring the measurement problem into the game, the problem here now with the calculation with vacuum fluctuations, which we have to understand is, okay, in ordinary experiments, we know that you can keep subatomic particles in a superposition on fairly wide length scales, right? So you can do interference patterns and all the kind of things that you do. But now what this calculation seems to be suggesting is that even those superpositions should not be visible if you treat the environment of vacuum fluctuations as an ordinary environment.
Mm-hmm.
But
so
okay, I mean, maybe
yeah, let us go on. Keep the discussion
so,
for the end.
Yeah, so the point is the following. So if I take this expression for the reduced density matrix literally, as I do in ordinary environment, so so for example, if I have a thermal bath, a thermal bath of photons, I do the same calculations. I see that the off-diagonal elements decay, and this in some sense gives me the standard measure of decoherence. So if I increase the temperature of the bath, the decoherence would be more, or the coherence length would be shorter. So in this sense, this calculation seems to be suggesting that in the presence of vacuum fluctuations, it's not super clear why we are able to see subatomic particles in a superpositions that we typically see in ordinary experiments, because the calculation seems to be suggesting is that the coherence length goes to 0 as long as you keep the cutoff as soon as you send the cutoff to infinity. So this is the first thing which we have to understand why this happens. So, I mean, the similar...
Can I ask a question? So, sorry to interrupt you again.
Yes.
But this rho r of 0, that's the initial density matrix for...
Yes.
So, and that contains the cross terms then?
Exactly.
Yeah.
And this is this is how the cross terms evolve in time.
Right. Okay. Yeah. Okay.
Essentially, I start with the... Okay. So this problem was also encountered by Barone and Caldera in this work, and their argument was that since from the very beginning, starting from the Lagrangian, since you are talking about a non-relativistic electron, the cutoff has to be such that it is much less than mc squared. So you are not allowed to take the cutoff to infinity. And so you keep a small enough value of this cutoff so that the calculations are safe. And that means that your coherence length would not go to 0. And then you can just say that, okay, this cutoff has to be small enough so that you are consistent with experiments that you see generally. So you can still explain double slit experiment in the presence of vacuum fluctuations by just having a lower value of omega max, motivated from the argument that the electron that you're looking at is a non-relativistic one. But for me, this argument is unsatisfactory because just from a point of principle, okay, even if the value of the cutoff, even if we are not allowed to take the value of the cutoff to infinity, there is no objective way to determine what this value should be. And if this value is arbitrary, then it should not be something which is observable, because if it's a true observable, there should be a way to really numerically determine the value of this cutoff, which we do not have. So for the purposes of the calculation, this omega max, as long as it's finite, at the same time, it's also completely arbitrary. So it seems a bit fishy to associate this decoherence effect to something which is observable. And this was, in fact, also what was concluded by Unruh in another work. So I will come to both these works. So beginning with Barone and Caldera, essentially their argument was, as I said, that you keep a small enough value of the cutoff, you have decoherence, but it's typically very small and would not be observable. And physically, they associate this decoherence effect to a picture that, okay, vacuum fluctuations kind of lead to a diffusion or some kind of a jiggling of the electron, and then it emits radiation, and that radiation carries Witch path information. Okay, so now the point is to understand equation 19. Technically, the only way, so technically this is the result. So the only way which I think one can use to resolve the paradox is to have a correct physical interpretation. So let's examine the physical interpretation of Caldera. They are suggesting that this decoherence effect is caused by the jiggling of the electron and the radiation that it emits subsequently, which then carries the Witch path information. So for me, this conclusion doesn't work because of the following. So one can show that this decoherence or the loss of coherence to the environment of vacuum fluctuation is reversible. So what one can do is to consider a fictitious situation in which I have a time-dependent charge. So we consider a situation in which the charged particle interacts with vacuum fluctuations for a finite period of time, capital T. And we slowly switch on the charge. So we say that the charge was zero in the beginning, and it was zero at the end of the process. And in the middle, we turned on the charge fully. So this F of T became 1. And we just do this low enough not to introduce any new physics into the picture. And with that, we found out that with this time-dependent charge, the original noise kernel, which was calculated for a constant charge, transforms in a specific way, which depends really on this profile of the function that you take. But quite generally, if one switches on this charge slowly enough, what we found is that this modified noise kernel, and therefore the modified coherence length, would have this relation, would have this expression. So 1 over omega max or k max is what we found out in the previous calculation. But now we see that this is multiplied by these boundary terms, f of 0 and f of capital T. And since we assume that the charge was switched off in the very beginning and switched off in the very end, we see that this denominator goes to 0 and the coherence length goes back to infinity, if I consider the case of a time-dependent charge interacting with vacuum fluctuations. So if you allow me to go back, if the coherence length goes back to infinity, we see that we recover the original density matrix. Yes, we recover the original density matrix that we started with. So the point is the following. If I consider a time-dependent charge such that it interacts with the environment of vacuum fluctuations for a finite time, and then switch off its interaction with the environment, I recover full coherence back into my system. So this decoherence factor, which we observed in the previous calculation, it cannot be due to the emission of Bremsstrahlung, because otherwise the information is carried away by this radiation and lost basically up to infinity, and it cannot be recovered in a reversible way just by switching on and off the interaction with the environment. So now if this decoherence factor, so at least equation 22 for me means that this decoherence factor that we observe cannot be physically due to an electron being shaken around by vacuum fluctuations and it emitting real photons up to infinity. So if it's not that, then what could it be? The answer is that it's actually due to the tracing over the dressed states of the electron. So a dressed electron in the QFT is essentially, if one wants to paint a picture, it would be that of a bare electron surrounded by a photon cloud. And one may mathematically treat these dressed states as coherent states. So for example, if I consider a coherent state alpha, and if I sort of expand in Fock space the vacuum of QED into a Fock space of different modes, all being in the vacuum state, I multiply with this operator, then I would have this relation with the inner product of two coherent states, right? So if now I considered a coherent state of the electromagnetic vacuum, for instance, if I act with this operator here, the same expression here, one can use to calculate this overlap, alpha R1 with alpha R2. And you see that you get the same decoherence factor that you saw in a full calculation before. So the point that I want to make here is that what is happening is that the interaction of the bare electron with the vacuum state is such that the state of the bare vacuum goes into the coherent vacuum state or the dressed vacuum state. And it is the dressed vacuum state that we have traced over in order to get this expression. However, this must not be done because as is known from a long time. In standard QFT, when we speak of an electron, we always have in mind a dressed electron. So this photon cloud that we are speaking about is actually what you observe with the electron. So you never, in principle, in typical experimental situations, you never really observe the bare electron. What you observe is the electron with its photon cloud. So the resolution to the paradox really is that the photon cloud that we have traced over, or the stressing which we have traced over, must physically be considered as part of the system rather than the environment. If one has a funny experiment in mind in which you can probe this dressing of the electron, then this expression to some extent could give you an estimate of why the decoherence that you are observing is. But in typical situations where we do not probe the dressing of the electron, the expression of the decoherence factor that we have obtained must be considered unphysical. Again, because the electron that we observe is typically with its dress states and not without its dressing. So with these two different independent analyses, the conclusion that we have is essentially that the decoherence factor that you get in the master equation should not be considered as something that you would observe in typical experimental situations, because it just corresponds to a tracing over the dressed states of the electron, which again in typical experimental situations is irrelevant. So the conclusion is that there is no decoherence due to vacuum fluctuations in ordinary experiments. You will not see that. And this is still interesting, not just from the, it's not just a hypothetical question. I think there are still some works which people do. For example, in the case of people are now studying how particles might decohere due to the presence of gravitational field. And they are testing some quantum signatures of gravitational field. And some people have considered the possibility that if you treat a gravitational field quantum mechanically, you would again have a finite decoherence effect due to the vacuum fluctuations of this gravitational field. But I think the same logic would apply there, that typically this decoherence factor that you observe is unphysical for the reasons that I've already said. Okay, so with this, I would move to the second, the shorter part of the talk, is basically radiation reaction. So again, we had three pieces to the master equation. One was the free evolution, one was the decoherence effect, which was essentially controlled by the noise kernel, and the third effect was the dissipation, which essentially tells you how the electron loses energy to the environment if it is accelerated. So in classical physics, we know that if you accelerate a neutral particle, it essentially just obeys Newton's law. So F equals ma. However, if you have a charged particle and if you accelerate it, we know from Larmor's formula that an accelerated charged particle emits radiation. And because of this emitted radiation, this radiation makes a back reaction on the electron, if you like. And this additional force, you can compute this classically, is given by the third time derivative of the position. So a accelerated charged particle experiences an additional force in comparison to the neutral particle, which is called the radiation reaction. And it's very interesting. I mean, the radiation reaction has certain interesting features. So for example, if you have a harmonic oscillator, if the external force is due to a harmonic oscillator, to leading order, you can rewrite this triple derivative term as minus omega naught squared. There is a squared missing. Minus omega naught squared x dot, which essentially tells you that this radiation reaction is nothing but a friction term. So you have a charged electron, you have an accelerated charged electron, it loses photons to the environment, which exerts a frictional force. So this would be a very basic understanding of this radiation reaction force. Then this equation as it is also tells you that if the electron is in uniform acceleration, this radiation reaction force would vanish, which is consistent with the equivalence principle. But then it poses some sort of a counterintuitive. So if I have uniform acceleration, and if we now say that this radiation reaction term this force would not be there, would it mean that there is no friction and therefore no emission of radiation for a uniformly accelerated charged particle? Because apparently that is in contradiction with Larmor's formula. But the answer is that the uniformly charged, uniformly accelerated particle, the energy that it loses in the form of radiation is compensated by the so-called short term. So there is no paradox. So a uniformly accelerated charged particle does emit radiation. It's just that it doesn't lose energy in this very specific situation. So, but okay, I don't want to go too much into the history of this radiation reaction force. Let's just come back to this formula here. So you have an accelerated charged particle and it experiences this additional recoil force, if you like. So the problem with this formula is essentially its homogeneous solution, where you see that even in the absence of any external potential, it features this accelerated, basically it would accelerate and exponentially. So the solution to this differential equation is unstable and unphysical, strictly speaking. So again, there have been historically many ways to think about this. One classic way is to imagine that the electron is actually a spherical shell of some radius r. And if you keep this radius big enough, you do not have this problem that we have. But for sure, for a point electron, the problem persists. Like you have these runaway solutions, which are unphysical. And at least a nice feature of the master equation that I obtained was that, so using the master equation, I could compute something like this. So what I'm calculating is the rate of change of, so acceleration of the expectation value of the position operator. And it turned out that the following expression is obtained. And again, I emphasize that the master equation is valid only to second order in the electric charge E. And now you see that if I switch off the external potential V, the system Hamiltonian would just reduce to P squared over 2m. And it is a very simple exercise to see that if you just substitute P squared over 2m in all three commutators, this term would also go to 0. So as soon as you switch off the external potential, this radiation reaction term would also go to 0, and there is no runaway solution up to second order in the interaction. Whereas if this V is not 0, you effectively get the same equation as the Abraham-Lorentz equation. So the particular solution of this differential equation would be the same as you would obtain classically. So this again, I mean, I'm not claiming too strongly that it solves the, let's say, this long-standing problem with the Abraham-Lorentz equation, but at least it seems that up to second order in the interaction, the master equation is, let's say, more physical than what you would typically have for the classical Abraham-Lorentz equation. Although the classical Abraham-Lorentz equation is exact in the sense that it's not expanded out to only second order in E. So it could be that this sort of resolution of the runaway solution that I have in the master equation could just be an artifact of the second order expansion, and maybe the problem still persists if one is in principle able to compute the master equation to all orders, but at least to second orders, things are consistent. Yeah. And I think with this, I think I'm towards the end of the talk. Yeah, thanks.
Thank you very much for this talk. So then let us open it up for questions, discussion. Whoever wants to ask a question, please raise your hand in the, well, just raise your hand. So what, first question is up to you.
Yeah, let me start with something, a simple question probably for you. Like if you can go back to this equation 16, I think it was.
Okay.
This evolution for the reduced density matrix. Just to understand it. Yeah.
Here or?
Yeah, that's fine.
Okay.
Like, what's this? So here you have an electron in a superposition of being at two locations.
Yes.
Okay. So, like, So one way I understand decoherence is, well, like, if you take the modulus squared of this electron, right, you're gonna see these cross terms. Okay, and so I thought the point of decoherence was to get rid of these cross terms in the modulus of psi squared.
Yes.
Okay. But like if I then look at 14, like modulus psi squared is just the diagonal elements of this density matrix.
No, I'm just explicitly writing out the off diagonal elements here, right? So decoherence kills only the off diagonal elements. So I'm explicitly.
But hang on. So is this the reduced density matrix on the left hand side?
Yes, rho R is the reduced density matrix.
Yeah. But let me look at the diagonal components of that, because that's the modulus of psi squared, right?
Okay. Yeah, I mean the diagonal
well,
components.
The modulus of psi squared
Then I have
doesn't
to go
change,
back to the original. So I mean, yeah.
If you go back to that 16.
Okay. I mean, the diagonal elements will not be captured here, right? Because then x prime is equal to x, and then this term.
But like on the level of psi squared, I would still see the cross terms. That's what I'm saying. So I want to understand this equation better.
Well, if the diagonal components at a later time t is the same as the diagonal component at the earlier time 0.
Exactly. So if I look at modulus psi squared,
yes,
it hasn't changed. So I have the cross terms at an initial time. I also have them at a later time.
I mean, it does not suppress really again. So the overall probability has to be 1. So if I sum psi squared x over all x, it has to still give you 1, right? The point of decoherence is that it only suppresses the off diagonal elements.
Right, but like I haven't.
Trace of rho for any open quantum system is still equal to 1, right?
Yeah, I'm not questioning that.
And this expression is ignoring the free evolution. So this is ignoring free evolution and everything, just the decoherence part. Okay.
Yeah, but so again, so like if I just look at the modulus of psi squared, right? If I have cross terms, so I have a superposition here of psi1 plus psi2. If I look at the modulus squared, I have the cross terms.
Yes.
Psi1 star times psi2 and the complex conjugate.
Okay.
I thought the decoherence you wanted would kill off these cross terms in the modulus of psi squared. And if there's suitable coupling to an environment, this will happen, right?
Yes.
So that basically the density of my electrons is just given by, if after tracing out the environment, is given by modulus psi1 squared plus modulus psi2 squared.
Yes, I agree.
But here I don't see, from equation 14, that's clear that won't happen.
Why wouldn't that happen? So
well, look at the case where x prime equals x. That gives you that gives you the position density for the electron, right?
Okay.
So if initially, so this exponential factor is then 1, okay?
Yes.
But so the initial position, if the initial position density contains the cross terms, then so will the final density.
No, the cross terms are when x prime is not equal to x, right? This is the cross term.
But by cross terms, I mean like psi1 star add x times psi2 add x.
Okay, maybe it's the matter of nomenclature. So for me, my full wave function psi is psi of x plus psi,
It's psi1 of x plus psi2 of x, right?
Yes, so yeah, okay. And now no, so my full, 1 second.
It's probably a basic confusion, right? That I have.
No, I mean, you have the full wave function psi, right? So now at x prime, it's just psi of x, and at x prime, it's just psi of x prime, right? I don't really see I don't understand I mean, if for example,
but like
let's say,
if I look at the position density of the electron.
So I write down my so the reduced density matrix is just like this bracket psi, and on the left hand side I act with x prime, and on the right hand side I acted with x, no? So this gives you psi x prime times psi x. And this is
right.
probability amplitude of it being able to be at x and x prime. And this is precisely what is killed by this expression. So rho r x prime x comma t is just psi x prime times psi x, where psi is the full wave function.
Sure.
And,
yeah.
and this is what is being suppressed by the time evolution. So I don't see why this is so if I consider the cross terms are precisely what is being suppressed by the environment.
Yeah,
So
we're meaning something. I'm talking about other cross terms than you are. I'm talking about cross terms in the position density, while you are talking about cross terms in the reduced density matrix.
But I mean the.
So I'm talking just about the position density for the electron, right? If I look at the modulus of psi squared.
Yeah. Okay. Okay. You are saying psi. Okay. Yeah. Yeah, because the electrons
would give you that your position density for the electron just becomes modulus of psi 1 squared plus modulus of psi 2 squared.
Yes. Yes.
So if I don't have any decoherence, it's gonna contain these cross terms, right?
Yes, it's gonna contain these cross terms. Yes.
On the position, on the level of the position density, right?
Mm-hmm.
I have terms in the density which are products of psi 1 and psi 2 at the same x.
Yes.
Okay. But like the position density doesn't change here according to 14.
No, because the electron is
on the level of the position density, because this exponential factor is 1.
Yeah, I mean, the electron is still half the times on the left and half the times on the right. So in that sense, the position density is not changing. So for
are you already assuming that there's just no overlap between psi 1 and psi 2?
Yeah, no, I think there's a. So let's say this overlap is killed completely. Let's say no. So.
But I mean, like spatial of just the way I'm talking on level of the wave function, right? So I have superposition.
Yeah.
Electron states, yeah. Are you maybe assuming they have no overlap in the first place?
No, initially they can have any overlap that you wish here.
Yeah. But the overlap is time independent, right? As your equation 14
initially. Lajos has some.
You want to?
I think you are talking about different things. This is 14 is an equation for a mixed state. There are no after the initial moment was already left. There is no more any wave function there. Only the density matrix, and it is in the position basis, and it is obvious that the probability distribution of the position is invariant. Only the interference terms are to go away. And this is an extremely popular equation in decoherence theory. I would say that it is the only relevant equation in theory of.
Yeah, I mean, for me, let's again, as Lajos said, like if you want to, in standard quantum mechanics, if you want to estimate the superposition-ness of a particle, so its capability of being at x prime and x at the same time, you just multiply the probability amplitudes first. So psi x prime times psi x. And if this term is 0, then you basically say that it cannot be in a superposition of x prime and x. And this is what 14 tells you.
I would agree.
Simply forget the wave function representation when you look at this equation 14. Even if you start, and this is what actually you do, you start from a superposition in a pure state, so in a double wave packet wave function, But immediately when you switch on this equation, you should forget about the wave function because the state becomes mixed.
Yeah, I think the confusion might be why has this something to do with superposition? So I mean, I agree this is probably the most important equation for decoherence, or maybe the only relevant one for decoherence theory. But I think it has no impact on the measurement problem, right?
No.
This is
no.
Exactly. Yeah, I think that's the only confusion. I think
no. I think that if you have, suppose you are in your lab and you are so smart, you prepare an electron or any heavier but still a microscopic particle in a superposition, a special superposition of two locations, and you are very smart, so you prepare a pure state, and then you realize that there are some noises coming from the environment, some background particles, some very rare thin gas or anything like that, and then you realize that what happens to the positional superposition of your particle, it is exactly what is described by 14. In the simplest case, of course. So this is typical what happens to an initial pure state superposition when you switch on the environmental effects. This is the prototype equation what happens to the initial double wave packet superposition. Of course, it is also relevant in measurement theory, but it happens in your lab whenever your pure state is getting under the influence on the environment, which is decohering your pure state. And this is the typical simplest paradigmatic equation to describe decoherence.
Yes, but I think the original problem, like if you have a psi that is composed by a superposition of psi 1 and psi 2, simply remains. I mean, of course, also in the discussion of the measurement problem, you apply decoherence to get rid of the psi 1, psi 2 scalar products, right? But this, I mean, the basic equation is still unitary, so you still have the measurement problem. So,
okay, maybe so in which sense do you say that the superposition remains? So if let's say from the point of view of an experimentalist, if for you superposition means that I see the interference pattern on my screen, if this is the way how practically you define your superposition, then superpositions would be suppressed. This is what equation 14 says. But if you say superposition in a more theoretic sense about, let's say, the global wave function, then I agree that the superpositions remain.
I mean, if I can annotate quickly, I can only do it with the mouse, it's going to look horrible. But if you have a psi, yeah, and I think this is also what Ward meant before, that is psi 1 plus psi 2. Yeah, and I think somehow the total, somehow the density matrix, I think you write probably like x, then total
psi 1 plus psi 2 x prime.
Psi x prime, yeah. So this is an equation that says something about x prime. But I think what is talking about, I mean, of course, you in psi 1, psi 2 in a measurement situation somehow where you have a big apparatus that interacts with the system. So this tends to go away, but you still have psi 1 squared and psi 2 squared. And there's no decision of if the cat is dead or alive, yeah. So of course decoherence is somehow needed to discuss these situations, but I mean the equation of motion that guides the system is this one, yeah. And if the equation of motion is unitary, then I mean forever it will maintain the superposition. And decoherence will not change that.
But what is, so let's say your psi1 is a Gaussian wave packet centered at x1, and psi2 is a Gaussian wave packet centered at x2, or you have something else in mind?
Yeah, take whatever you like, a dead cat and a live cat, for example.
Okay, but then the point is that if your psi1 is a Gaussian wave packet centered at x1 and psi2 a Gaussian wave packet centered at x2, and there is some initial overlap between those Gaussian wave packets, or in other words, x1 minus x2 is smaller than the standard deviation of the Gaussians, then this overlap is killed of the
yes.
Yeah,
as well as, for example, the overlap of a dead and a live cat is killed, right?
Yeah. Yes.
This is good that we have a mechanism like that, but it doesn't solve the measurement problem.
It doesn't tell you whether you will find it dead or alive. It will not, it says that it will be in a state where it's either dead or alive. It's not the two at the same time. It doesn't tell you uniquely whether, if you do the experiment now, whether it does not localize the wave function to a definitive outcome. I mean, it's what Laios said. It's essentially now a mixed state, not a pure state. So this is all the matrix tells you.
Yeah, it helps you in the computation, but it has no impact on the. But I think there's someone waiting for.
Yeah, let's call Julia, please.
Yes, I don't know if you can hear me.
Yes, perfect.
Yes, so thank you very much for this talk. I mostly, I think, agree with your conclusion about the role of the bare electron and the dress states. One thing that I would like to ask is, in one of your slides, you show relativistic effect that you neglected.
Yes.
So one of your formula, could you go back to this something like that? Because I think this is particularly interesting, because this is looking like that you could get violation outside of the light cone. This formula is looking like the Feynman propagator or square. But you have additional cutoff terms, of course. But if you consider this, it looks like it's another argumentation to say that this formula should be unphysical, because you will get something like possibility to communicate faster than light. I think if you have two electrons and you have this kind of system, then you will have a way to violate Bell inequality, but in a very strange way. And probably it's related to the old Fermi problem, also communication between two electrons. It has been discussed many times in literature.
So I would say, I think maybe, so I understand what you mean. So the problem here is that what I'm modeling is a point particle interacting with a field. And this is a bit subtle. So if I just considered a fermionic field interacting with electromagnetic field, then this problem would be a bit, easier to deal with. So what you should really understand are, let's say I have an electron, and what these are is this xt1 minus xt2, okay? So I would really, in this particular setting, understand xt2 as xt1 plus the velocity of the electron, like a semi-classical analysis, if you like, where I insert as the spatial arguments within the field operators, the position of the electron in a classical sense. Of course, the electron in principle is a wave packet, so the meaning of x, which enters the operators, is a bit fuzzy. But I think this is the best you can do if you want to treat a point particle interacting with a field. So you should really think of this r as the distance that the electron travels within time t1 and t2. So if you do not want to do this, which I can see why you might have problems with this, the only way out is to do a full relativistic calculations in which also you treat the electron as a field. But then things go out of hand. Like, it's not worth doing, I think. If I mean, it's worth doing if you're really interested in relativistic effect. But,
but it could be probably interesting, because to see how far you can go with your analysis to show this kind of paradox, because it reminds me of an old paper by this guy called James Frenzon. He published a paper called, I think it was generation of entanglement side of the light cone. That was a bit crazy, but the argumentation that he used is very similar to you in the end. That dress states is able to solve the problems.
I will look at it.
Yeah, I think it's a remark, and it's very interesting.
Yeah,
what you do. Thank you. Okay.
Okay, thanks. So is there another question? So otherwise, let's thank you again.
Paula, one more question.
Yeah. You have another question. Okay.
Yeah. A bit more open question, Anirudh. So what's your conclusion? Is now the QD vacuum a possible source or not for driving this CSL models?
To drive these CS? No, I would not. No.
Okay.
Yes.
Okay.
But you see, like, it's a bit more, I mean, okay, there is another technical, so the way that Breuer and Petruccioni do the calculations, it's perfectly fine. So, but it's really subtle, the problem. Like, I don't want to, like the way I started the talk, quoting them and saying that they are wrong. I mean, with all due respect, because the calculation that they do is fine, and it's really a subtle point. And it's, because if you just take the master equation literally, it's a bit non-trivial to understand why this decoherence factor should not be considered as something physical. So.
Okay. Yeah, thank you very much.
Okay. So there's something in the chat. Yeah, you read that. Okay. So if there's no further question, then let's thank the speaker again. And thank you for this talk. And yeah, next week we will continue with Jakob Barandis, I think. What do you want to announce next week's talk, or?
No, yeah, I mean, we could, you did it basically. Yeah, so new prospects for causally local formulation of quantum theory. What I think you checked with him that about the talk, and maybe what you will also host it, right?
Yeah, that's fine for me.
Okay.
Yeah.
Okay. Yeah, so looking forward to see all of you again. Thank you very much for presenting today, Anirudh.
Thanks
for bearing all our questions.
No, it was fine.
Okay. Yeah, then see each other soon.
And say hello to Angelo if you meet him.
Yeah, sure. Okay.
Yeah, and by the way, I think Fabian and I will be down around May, because I think Matteo invited us, or at least me, and I might bring Fabian along. Then we can still talk a little bit about this decoherence and
okay. When? Next month? Or
I think in May we're going to be.
May. Okay.
Yes. Yeah. All right.
Okay.
See you around. Bye.
Bye. Thanks.